So why I have defined this space? Because I want to define Sobolev space with zero boundary value. Zero boundary value. So you can see, because we have taken all those functions which has compact support in omega, this means that in any set omega, hello. In any set omega, you can approximate your given Sobolev function with a compactly supported function. This means that on the boundary, they have value 0. So that's why I'm saying that this space W01P is actually a Sobolev space which has 0 boundary value. Okay. And now, what is the difference between W01P omega and W1P omega? So it is clear by definition that this is completion of CC infinity functions. And we have seen in the previous lecture that every Sobolev function can be approximated with smooth function. So W1P is the completion of this space and W01P is the completion of this space. Okay. So here I wanted to define the Sobolev space with boundary 0 value. And now we will come to this, we will see Sobolev inequality. So I will talk about Sobolev inequality. I will start with first Gagliardo Nirenberg-Sobolev inequality. This is the first inequality we will encounter. Second one will be Poincare inequality. And third will be Morrey's inequality. So don't confuse, all these three inequalities are the properties of domain. It's not a property of Sobolev space. Okay, so let's start with first inequality. So first one, Gagliardo Nirenberg-Sobolev. Sobolev inequality, I will call this GNS inequality. Okay. So what this inequality say? Let 1 less than equal to p less than n. This is the exponent I have fixed for p. Then there exists a constant c, and that depend on this dimension np, such that I have np over n minus p integral is less than equal to I can control this this norm with derivative LP norm. And this is true for all function u in W0. W1P Rn. So this is, you can see here, when the domain is Rn, then we have a strong inequality. This is very strong in some sense. We will see why this is strong. And you can see that by this inequality, W1P Rn is continuously embedded in L np over n minus p. Why? Because I have controlled this np over n minus p norm with W1P norm. So this is continuously embedded in lnp over n minus p. We take a notation here. So for 1 less than equal to p less than n, I will call this np over n minus p value hp star. And in every textbook, most of the textbook, this p star is called as a Sobolev conjugate, called Sobolev conjugate of p. The only thing we have to notice that this exponent p star is positive only in when p is between 1 and n. So that's why we have taken the restriction on p that it should be in 1 and to n. Then this p star value is finite. Okay. Any question? Okay. So some observation from GNS inequality. The first one is, if U belongs to W1P Rn, then U also belongs to LP Rn by definition, and by embedding it belongs to LP star of Rn. So here you have a better integrability because P star is always greater than P when P is less than N greater. In fact, P star is always greater than P in any sense. When P is less than infinity also, then P star is greater than P, because then P star tends to infinity if P is less than equal to N. And then second one, if U belongs to Sobolev space W1P Rn with this P exponent and the derivative is 0 in Rn, then we have, then this GNS inequality shows that my function U is also almost everywhere 0 in Rn. Why? Because we have this UP star norm of U is controlled by some constant time P norm of du, and this is 0 almost everywhere. This means that this integral is also 0 almost everywhere. So here you can see that you have a bound for LP star functions with derivative p norm of the derivative. So here the function has 0 derivative, but here you have function has 1 derivative. So this is kind of, we have seen this in fundamental theorem of calculus, that this right hand side we have function which has no derivative, but left hand side we have this derivative involved. Okay. And now we have third observation, that W1P local Rn, this is also embedded in LP star locally Rn. So how to prove this? So let omega, which is compactly contained in Rn, and you have to show that if you take a function from here, and you have to show that this function should belongs to this space, this means that the function LP star norm is finite. So let U belongs to W1P log Rn. This means that this is locally LP integrable on Rn. This means that for any compactly contained subset, your function U is LP and your derivative is also in LP. So this means that U is in LP on omega, and all the partial derivatives first order is also in LP on omega. And now choose a CC infinity function which has compact support such that eta is equal to 1 on omega. So then you can eta u, you multiply this cutoff function with your original function. This is in W01P Rn. And then you can apply directly, here you apply GNS inequality to conclude that due LP star norm of Rn is controlled by eta u LP star, of omega is controlled by LP star of Rn, and this is less than equal to by GNS some constants time t eta u of LP of Rn, and which we wanted to prove that for every compact support we have control, this norm is bounded. LP star norm is bounded because this is this is bounded because eta u is in W01P. This means that on the boundary this vanish. So this norm is finite. Yeah. Any doubt? So why I multiply this function with eta to make sure that this eta u is in W01P Rn, because I have till now this GNS inequality for W1P Rn, but we have to control this norm. And here I'm using one more, that W01P Rn is same as W1P Rn. This we haven't seen it, but so this means that this belongs to W1P Rn also. Okay. Any question? Is everything fine? Can you hear me?
Yes.
Is everything fine or should I explain
Yes,
some?
yes. Now,
So now fifth one is this uh, Gagliardo Nirenberg-Sobolev inequality. This also holds for higher order. Higher order WKP. The statement is let K belongs to N, and then I have P N by K. So whenever I am rising this K, initially we had K is equal to 1. So here we have exponent P between 1 to N. But whenever I am rising K, I have to lose my exponent. So here the P is shorter because P is less than N by K. Then there exists a constant C which depend on N, P, and K such that UP star 1 over P star, this is bounded by some constant times du 1 over P. And this holds for all U in our Sobolev space WKP. So here this dku is kth weak derivative. Weak derivative. So dku means you have k is equal to something alpha 1, alpha 2 to alpha n, where, yeah, k is equal to this, where alpha 1 plus alpha 2, the sum is equal to k. And this derivative is dku LP norm of Rn. This is actually summation of d all these k not here k j of u LP norm of Rn, where mod of j is equal to k. So this is my dku LP norm. So don't confuse with notation. This is just a notation, but the meaning is this, that you are adding all those k order derivative LP norm here. This is only LP norm of kth order derivative of your function u. This is just a notation. This doesn't mean anything if you don't know that what here we are doing. We are adding all those k order derivative LP norm. So this GNS, it has been proved by, first it was proved by Gagliardo Nirenberg, and then Sobolev has modified it. So that's why it is called Gagliardo Nirenberg-Sobolev inequality. And here one thing is to remember that I am taking domain Rn everywhere. I have not used any proper subset of Rn. In this inequality, everywhere I am using Rn. Okay. So let's see corollary. So corollary is, let we have exponent p between this range, and now omega is a subset of Rn open. So in the first lecture, I have defined that the Sobolev space is only defined on an open set. So if omega is proper subset of Rn, it should be open by the adjunction to get the definition of a Sobolev space. So now here I assume that U is in W01P is such that the derivative is 0 almost everywhere on omega. Then we have U is equal to 0 almost everywhere in omega. Okay, so how to prove this? You can see my function is vanishing near the boundary because we are approximating this W01P by CC infinity function, and each CC infinity function has 0 value on the boundary. So function should have 0 value on the boundary. So suppose this is my set omega, and here is my W01P function. So here the value is 0. I will extend this function by 0. So I will extend my U by U tilde by extend U tilde, extend U by 0 outside omega. Then your function U tilde by extending U tilde will be in W1P of Rn. And now you have, for any Sobolev function in Rn, you have GNR inequality. So now you can use GNS inequality to get this UP star 1 over P star U tilde is less than equal to some constant times DUP star. And we have that du is 0 almost everywhere in omega. And since we have extended our function u by 0 outside omega, this means that everywhere my integral is 0. So this means that on a this means that u tilde is 0 almost everywhere in omega in Rn. And we know that U tilde is 0 almost everywhere outside omega. This means that U is 0 almost everywhere in omega also. This implies that U is 0 almost everywhere in omega. So here the main key point was that we are able to extend our function by 0 because it was taking value 0 at boundary. So there is nothing harm to break the continuity or break the differentiability by extending the same value whatever the function has taken at the boundary. So this was the only key point. Okay. And now we will see one interesting remark. So when we have P in this range, then we have defined P star is NP over N minus P. So you can see that when P approaches to N minus, then P star approaches to infinity. And whenever this we can get from this definition, and by G and S inequality, we have that W1P Rn is continuously embedded in LP star of Rn. So we can expect that when P is tending to N star, W1P of Rn should continuously embedded in L infinity of Rn, because then P star tends to infinity. But this is not true. This is false. So I have an example. So you can see that this function, when P is equal to N, when P is equal to N, you can construct this B01 subset of Rn. Ux is, this is very famous example, log 1 plus 1 over mod x, when mod x belongs to, when x belongs to B01 minus 0, and this is 0 on single 0. You can check this function u belongs to W1n over B01, but clearly this function is not in L infinity, because in every open neighborhood of 0, your function blow up by logarithms. And this should be greater or equal to. Any question?
Actually, first remark, one less than equal to p less than n, and you choose, for example, when p equal to n, that p are same.
I said that when P is equal to N, you expect that your function should be in L infinity,
Okay, okay.
but here your function is not in L infinity.
Okay.
Yeah. Okay. Now, this corollary, we will see then another corollary where I will talk about uh, for all P in between 1 to infinity. So initially we see G and S only for P in this 1 to n range, but I will write something very strange, which is in, I will write an inequality which hold for all P in this range. Okay, so let's see. The statement goes like, when let P is 1 to infinity and omega subset of Rn open with finite measure. So here we have taken this measure should be finite because we want to use Hölder inequality in the proof. And assume that U is in W0 1P of omega, and let 1 is less than equal to Q less than equal to P star for 1 less than equal to P less than N. And for P greater equal N less than infinity, I will assume that 1 is less than Q varies from this range. So this Q varies 1 to P star if P is in this range, and this Q varies all 1 to infinity if I have taken P in greater equal N. Then there exists a constant C which depends on N, P, Q such that we have this G and S inequality. So this is something strange. We have idea only for this from previous corollary. Means by using we have that by previous corollary we have that this P star is less than equal to DUP 1 over P. This is, yeah. And since omega has finite measure, you can go down all those Q which is less than P star. So this you can get it by free, but this case you have to use this technique to prove for second case. So this corollary is an easy exercise. You can try it by yourself because here I am just using Helder's inequality and G and S inequality twice. Okay, I will not prove it. I have proof, I will upload it, but I don't have time till now to prove it. So you can see the proof later. Now we will see something. Now we will see Sobolev-Poincare inequality. All these inequality are the properties of domain. This is not a property of a Sobolev space, LP functions. This is properties of your domain where your function is defined. So the statement follows, assume that omega is subset of Rn, is bounded, and 1 is less than equal to P less than P. Then there exists a constant C that depend on P such that your LP norm of your function is controlled by, now here you have better exponent. Amit, can you please unmute?
Hello. Can you mute him?
I can
Hello,
see.
Amit. Can you please mute yourself?
Yeah, I think it's fine now.
Okay.
So this is Poincare inequality. And here you can see that this constant is a better version because here your constant will not depend on your dimension. It's diameter of omega to the power n. So it is an explicit constant you get here. So that's why this Sobolev-Poincare is a strong version of your G and S inequality. And here it is stronger in one sense also that here there is no restriction on P. Here your P is from 1 to infinity, but in G and S inequality, your P was this. So this Sobolev-Poincare is something very stronger inequality, which we will get for zero boundary value Sobolev functions. Okay. So some remark of this Poincare inequalities. First one, that you can see here, if your function derivative is zero almost everywhere, then this inequality gives that your function is also zero almost everywhere, same as what GNS gave us. So if my function du is zero almost everywhere, then u is also zero almost everywhere. But this is for when u is in W0, 1p, because then only then you apply the Poincare inequality. But for GNS, you apply for W1p Rn. There is no condition that here the function should be zero on the boundary. Yeah. So now I will write Poincare inequality on cubes, which I have used many times on when you extend your function. So this is very useful Poincare inequality. So let u belongs to omega. U is open subset of Rn, means domain, and assume u is W1p locally with p in 1 to infinity range. Then we have a constant c that depend on n and p, such that now we are not talking about W01p. We are talking about W1p. So on the boundary, function can be very weird. That's why we are subtracting the average value. So by subtracting the average value, the function is zero on the boundary. So QXL 1p, this is less than equal to C times L QXL DUP 1 over p. Here QXL is a cube centered at X, and the edge length is L, and UQXL is the average value of Q, means this measure of this Q, integral QXL mod U dy. So QXL, the average value of U over this Q, and QXL is a cube that's centered at X and with edge length
Hello.
L. Yes?
No, I heard some sound, that's why.
Okay. And QXL is those cubes which completely contain in omega. So this is something local version of Poincare inequality. So what it say here actually, that you have, if you are in a domain omega, you restrict your function on this cube. Then you can apply the Poincare inequality on your function restricted over this cube, and you can get the better constant. Here the diameter of Q is root n times L, which root n comes to C. So L is the edge length of Q. So this is local version of Poincare on cube. Any doubt? Okay. So what we will get by this Poincare, we can see that if my function derivative is very small, then we can see here that the oscillation of my function from its average value is very small. And this is something same with Lebesgue differentiation theorem, where when Lebesgue differentiation theorem for LP, that for U belongs to LP, then if X is a Lebesgue point, then your function value is just this value. So your function in LP case, on almost everywhere, your function value is same as your average value limit. And something similar also happens here, that your function difference, your function cannot be very large from the average value when the function derivative is very small. So you can control the oscillation of your function from its average value by its derivative. So this is something is strong in local sense, that locally of your function cannot be very weird. It cannot blow up because the average value is controlled by your function, or your function is controlled by your average value. Okay. And now again one more Sobolev-Poincare. Sobolev-Poincare inequality in Q. So this is, let's say, omega is subset of Rn. U belongs to W1P locally. And here I am assuming that P is between this to this range. So that's why this critical exponent calls this inequality as Sobolev, because now the Sobolev conjugate will come in the game. So then there exists a C which is depend on N and P, such that you have this UQXL P star 1 over P star is less than equal to C times L QX 2L PUP 1 over P. Here is QXL. And this whenever QXL is compactly contained in omega. So initially we have P here. And we know that when P star is always greater than P. So this inequality shows that we can control P star norm actually. This means that we have better integrability of U minus average. So this is Sobolev-Poincare is stronger than Poincare on Q, because now we have improved the integrability of our this side of. Okay. So some remark. I think Amit has some problem with the mic.
Can you mute him? Like,
I have to go back. That's why I'm not.
just try if you can.
Yeah, I think I can. Yeah.
Okay.
So the first remark from Sobolev-Poincare inequality, that it shows W1P locally Rn function. They are compactly contained, or they are subset of LP star local function when 1 less than P less than N. And the second, we have seen that it is stronger than Poincare on cubes, because P star is always greater than P. Okay. So in the next 10 minutes, I will introduce Morrey's inequality.
Riddhi,
Huh?
I have one question.
Huh?
So, like, what kind of domain satisfies these kind of inequalities?
Yeah, so I think
If you can give some like easy kind of
So-
example which we can see.
okay, so first you can see disk, balls. All
Mhm.
balls in Rn is Poincare domain.
What is Poincare domain?
Then domain having this Poincare.
Okay. Okay, in the whole domain or
I
in the
have
cube?
to. Okay, so this is where I have written. Yeah, so this you can say that this is PP Poincare,
Okay.
because you have P here and P here. There is a lot of version of 1P Poincare,
Mm-hmm.
QP Poincare.
Okay.
So here I'm taking Poincare domain, means I have PP Poincare city, PP Poincare domain. So all balls are Poincare domain, and I think Koskela has proved something. If my domain is bounded,
Mm-hmm.
domain is bounded and domain is Poincare, then W1P extension is if and only if L1P extension. So here W1P extension means you can define an extension operator from W1P omega to W1P Rn.
Mm-hmm.
And here L1P extension means you have defined extension operator from L1P omega to L1P Rn. And here L1P is
So in
L1.
the sense that these are the like domains which have this extension property.
Yeah, yes, equivalence extension
Hmm.
property. And L1P is homogeneous Sobolev space that you have only the gradient norm. And
Mhm.
recently, me and Koskela has proved that there exists W1P, W1Q extension domain,
Mhm.
where 1 less than Q less than P less than infinity extension domain, which is not L1P, L1Q extension domain for Q, sorry.
Okay, so means these domains can't be Poincare domains.
Equal to N. Huh? What?
So these domains, like this domain
Uh-huh.
cannot be Poincare, na?
This domain cannot be Poincare. We
Yeah.
have shown that if we have an extension to control the extension operator, it should be blow up, and we saw that it blow up because of we don't have Poincare.
Okay. Mhm. Okay, thank you.
Yeah. And the Morrey's, so last thing is Morrey's inequality. So let A subset of Rn and U be.
Yeah, just one more doubt, Riddhi.
Mhm.
So, like in the definition of Poincare domain, like just a small doubt. So, it should be a finite volume, na? Let D be a domain in Rn, so it should be
Yeah,
a finite volume.
Yes.
Okay.
Poincare is always for a bounded domain. Here, your domain should be bounded. Sorry, this is not Poincare. This is Poincare. So your domain should be bounded. You can see this constant functions. So if U is constant, then constant function in Rn, then you have control here, but you don't have control here. Because the derivative is 0 almost everywhere, and you have control here. This integral is always 0, but the LP integral of constant function over Rn, this should be blow up. So this means that your function should be in a bounded domain.
Okay.
Okay. Morrey's inequality is refers as Hölder's inequality, and it says that if my P is greater than N, then W1P is contained in C0 alpha, where alpha is 1 minus N by P. Or let's say we do for Rn only, because when we bound the space, this is not in general true. So Morrey's inequality says that my Sobolev function is embedded in a Hölder continuous space, which is C0 alpha. Means all my functions here are actually Hölder continuous functions. And interesting part is this, your Hölder continuous functions are very nice. So if our function U is in W1P is this space omega, then when P is less than N, then you have a small measure set 0. Your function can take any value and a small measure 0 set. But this is true only for P less than N. When P is greater than N, then this possibility cannot be whole. Means your function doesn't have this kind of tentacles in a small measure set 0, because that it is properties of Hölder continuous function. That if your function is Hölder continuous almost everywhere in omega, then you can extend your function U tilde, which is Hölder continuous everywhere. So Hölder continuous is very, very nice property for a function. Means Hölder continuous function can ignore a measure set 0, how to say, set of measure 0, your function is not good. But this cannot be true. If your function is Hölder continuous, then your function is Hölder continuous everywhere. Means you can extend your function on a measure set 0, measure 0 set. Because how you do this, you know that ux minus uy is less than equal to some constant times mod x minus y, 1 minus n by p. This is if u is in W1P Rn, and p is greater than n. And now almost everywhere it is true, but you can see if you take a point x is in a measure zero set where your function is not held or continuous, then you can approximate this point with a sequence. And you can, with a Cauchy sequence, and you can see that your uxn will be also Cauchy. Will be Cauchy, you know, Rn. This means that this sequence uxn should be convergent because W1P is a Banach space. So you can transfer the value to x by limit of this uxn. So you can define function u tilde on x, which is limit of uxn and goes to infinity. And you can see that this extension is actually a Helder continuous extension. Yeah, I will stop now.
Yeah, so do we have any question? Hello?
Hello.
Hmm.
Hello.
Yeah, can you please speak a little bit louder?
Hello. Can you hear me?
Yeah.
Yes. So we have these constants in all inequalities. For example, I pick let GNS I pick if I. So is there a estimate on C or we don't care about it?
C
C.
is the constant that depend on the dimension and the exponent p.
Now, do we precisely calculate that or you are bound on?
We have calculated when we are proving Poincare that you have removed the dimension and your constant is depend only on p. So basically this constant dependent comes from Helder inequality. So when your domain has finite measure, then your LP is embedded in LQ whenever P is less than Q. So this can be proved by using Helder's inequality. And here the constant will be something omega, a measure of omega to the power something by using Helder's inequality. So that's why this constant is depending on the dimension n. But for the Poincare, this constant is diameter of the domain to the power p.
Oh, okay.
Yeah.
Thanks. I have another question.
Mm-hmm.
So we prove this like all our embeddings, right?
Mm-hmm.
Like proving better integrability. So
Mm-hmm.
so where do we go from this? Like where do you use this? But like in PDs,
Mm-hmm.
what do you use that exactly?
Where do we use? You know that your function is in LP, but
Yes.
if somewhere you want to calculate higher integrability, means now you are calculating LP star, which is P star is greater than P. You don't know anything about it. That if your function is in LP, then it can be in LP star or it can not be in LP star because P star is greater than P. But when we are working in Sobolev class, then if your function is in LP, where P is less than N, then by Sobolev embedding, we know that our function is in LP star. So we have a better integrability of our function. And this we used manywhere in extension theorem. To find the exponent where your function cannot be extended beyond this exponent. So this I have seen only in Sobolev theory. I haven't seen in anything application in the PDs, but in Sobolev theory for the extension problems, we use this exponent to find out whether the function can be extended or not extended.
Okay, thanks.
Yeah.
Any other question? Okay, so we don't have any question.
Okay.
Thank you, Riddhi, for your
Thank
talk.
you. Bye.
So, yeah. We'll meet next week.
Okay.
Bye.
Bye.